Hello everyone, and welcome back to the Physics Basement, where today we're going to talk about Newtonian mechanics. We're finally there, the heart of Physics 1. Alright, so let's talk about Newton's laws. So there are a few limits to Newton's laws, okay, just a few. One, you can't use Newton's laws if you're talking about things that are traveling something approaching the speed of light, like some substantial fraction of the speed of light, then you need special relativity. You can't use Newton's laws if you're talking about something so small that it's down to, say, the atomic scale. Something has to, at that level, you need to use quantum mechanics. And with incredibly large gravitational fields, say the gravitational field on Mercury due to the sun, for example, then you need general relativity to describe gravity. But outside of those three regimes, which includes basically everything at the normal human scale, you can describe the dynamics of any kind of human scale system using Newton's laws. So they're incredibly powerful tools. All right, so let's talk about Newton's three laws. I use N1, N2, and N3 to denote Newton's three laws. Newton's first law: an object in motion remains in motion, and an object at rest remains at rest unless acted upon by an outside force. So there is, this is sometimes called the law of inertia. It just says that accelerations or changes in velocity are brought about by forces, and forces are, those pushes and pulls and things. This only holds in what we call an inertial reference frame. Basically, it's just non-accelerating reference frames. Those are inertial reference frames. So, for an example, just take an example. Let's say that you're driving in your car. Let's say you're driving in your car, and you come up to a stoplight, so you stop, you hit the brakes, and you have a can of soda sitting on your dashboard or something. You stop at the red light, and the soda can slides forward and spills all over the place. Okay, from your reference frame, the reference frame of you sitting inside of the car, you will actually not see a force on that can, even though the can will accelerate. So the reason why is because you're in a non-inertial reference frame. When you're sitting in the reference frame of the car, the acceleration that the car experiences is part of your reference frame. So from your point of view, you don't see this external force that's bringing about this acceleration on the can. Now, if you were to take somebody else who's standing in an inertial reference frame, they're standing outside of that car and watching this happen, they will see that since they're in this inertial reference frame outside, where Newton's first law holds, they will see that as you pump the brakes, that there's this force exerted on your car. It's the force of friction from the road, between the road and the tires. They will see this force get applied to your car, but not to the can of soda. So when the can of soda slides forward, that makes perfect sense to that person because they're in an inertial reference frame. Since you're sitting in the car in a reference frame that is itself accelerating, Newton's first law is not going to hold. So our definition of an inertial reference frame is just one where Newton's first law holds. Okay. So one more example. So the Earth is spinning. But that's okay that the Earth is not a perfect inertial reference frame. So on the scale of human-sized physics, you're not going to have to worry about this for the most part. So I can do a bunch of experiments in my basement down here, and I can treat this as an inertial reference frame, and that would be totally fine, right? The rotation of the Earth is not something that you need to account for unless you're talking about really, really far distance scales. So this is a perfectly fine inertial reference frame, and for the most part, we'll be doing a lot of problems where the kind of implied reference frame is just that you're sitting there on the Earth and that the rotation of the Earth is not actually affecting anything. Okay, so that was a bit about Newton's first law. Let's move on to talking about Newton's second law. Now, Newton's second law is going to be really important for this class, and for many of you it's going to be very important to your subsequent classes. as well. I think I've already said this, but if you're a mechanical engineering major, it's going to be your life until you're graduated here. So Newton's second law says that the net force on an object is equal to its mass times its acceleration. Now, this is a vector relationship. That means that both the magnitude and the direction are equal to one another, right? And the x component of force, that's going to be equal to m times the x component of acceleration. I can take the y component of force, that's also equal to, right, mass times, in this case, the y component of acceleration. Okay. Now, the SI unit of force is a Newton, right? A Newton is 1 kilogram meter per second squared. There's a few caveats that I just want to make sure you know about when it comes to Newton's second law. First is that this F equals ma formalism is only going to work if we have, in the case of constant mass, okay? This is where mass is constant. So if mass is not constant, it's a little bit more complicated. So strictly speaking, Newton's second law should be that F net is equal to the time derivative of momentum. Momentum is mass times velocity. Okay, in the case where mass is constant, then that just means that mass is F net is equal to ma. Another thing that you should know is that we're talking about here about strictly translational motion. So we're not talking about any forces bringing about rotational motion here, not yet. We'll get to that in chapter 10. So for right now, everything is linear, it's translational. Okay, this is Newton's second law. Mass here then is what is the resistance to acceleration for a given force. There's kind of two different ways to talk about mass. Mass could be thought of as the amount of stuff that something is made up of. Mass could also be talked about as just in its inertial properties, its resistance to acceleration for a given force. One of the reasons why we have this special limitation that you have to talk about things that are moving slowly compared to the speed of light is because at that point where things start to move close to approaching the speed of light, then those two definitions of mass actually are two different mathematical things. So it's kind of interesting. Anyway, so F net equals ma. Now remember, this is a net force. So that means you need to sum up all of the individual forces on an object if you want to get its acceleration. Just some of the forces will not do it for you. You have to get them all. Okay, let's do a really simple, quick example problem, and then I'll talk about free body diagrams. Okay, really quick example problem. Here's a baseball. So if I take this baseball, I'm going to try to make this as one-dimensional as I possibly can. If I take this baseball and I just throw it, I'm going to throw it like a dart. Okay, so that didn't break anything too badly. Now, let's just talk about the force, the average force that I exert on this baseball. And I'm going to make a whole bunch of really simplifying assumptions. Let's just say that I took the thing, right, it started out at rest, and I threw it. Let's say that my arm moved 0.3 meters. Okay, its initial velocity was 0, right? It started out at rest. And its final velocity was, say, 30 meters per second. Probably wasn't that fast, but close enough. All right, now what's the average force that my hand exerted on that ball? Well, I know that force is mass times acceleration. Okay, I also know that baseballs are approximately, have an approximate mass of about 0.15 kilograms. All right. So let's get the average force. I can get the average force from something like the average acceleration, right? The acceleration is not actually constant as I'm throwing this thing across, but on average, this is a pretty good approximation to say that the acceleration was basically constant. So in the case of constant acceleration, right, I can use the kinematic equations at constant acceleration. when I know the initial velocity and I know the final velocity and I know the distance over which the velocity changed, then I can use this equation where velocity final squared is equal to velocity initial squared plus 2a change in x. Okay, that, just putting in numbers here, that's 30 meters per second squared equals, the initial velocity was 1, right? So that term goes away. So that equals 2 times a times 0.3 meters. Or in other words, acceleration equals 30 meters per second squared divided by 2 times 0.3 meters. Okay, and if I plug this into my calculator, this will say 1500 meters per second squared. So I know the mass and I know the acceleration. If I take 1500 meters per second squared times 0.15 kilograms, put that in my calculator, I get 225 newtons. Okay, finally, let's talk about Newton's third law. So Newton's third law is sometimes stated for every action there's an equal and opposite reaction, but the better way to write it is say that the force that's exerted on body 1 by body 2 is equal and opposite to the force that's exerted on body 2 by body 1. Okay, now notice here the way that the indices are ordered is important, okay? This says, this is referring to the force on body 1 by body 2. This is referring to the force on body 2 by body 1. So you can see that these two forces are equal in magnitude and opposite in direction. They're called Newton's third law pairs. They're equal to and opposite of one another. So let's say, okay, here I have a hammer. And if I set it on this board here, there is a force that the hammer exerts on the board, and there's a force that the board exerts on the hammer, right? And this is pretty easy, should be pretty easy for you to buy that these are equal and opposite forces, right? The weight of the hammer pushing down on the board pushes straight down. The force that the board exerts on the hammer pushes straight up, right? Makes sense that they're equal to each other, right? Because nothing's accelerating, and they're opposite in direction. Right? Okay, so Newton's third law is pretty easy to buy in this case, right? Okay, now what if I take this thing, and I now make the system not static anymore? I bring about an acceleration. Okay, so I'm going to take a force and exert it on this board. I'm going to try really hard not to break anything. Okay, so now that time I hit the board and it accelerated. But Newton's third law is still true, even in the case of where something is accelerating. The force that I exerted on that board with this hammer was exactly equal and opposite to the force that the board exerted back on this hammer. Now, it might not have looked like there was much of a force being exerted on this hammer, but there was, and I could feel it, because I could feel it recoil when I hit that thing. So it's a little bit harder to imagine in that case, but Newton's third law is still true in the case where something brings about an acceleration. What's even harder to imagine is that for non-contact forces, Newton's third law is also true. So, talk about the gravitational force, okay? The Earth exerts a gravitational force on me, and I also exert an equal and opposite force to that on the Earth. So the Earth pulls down on me, and I pull up on the Earth, right? This is very hard for us to imagine because even though it's obvious that the Earth pulls down on me, it's not obvious that I pull up on the Earth. But that really is true. If you know Newton's third law and you know that it always holds, that won't be surprising to you. Okay, little conceptual question for you guys using Newton's third law. So let's say you're out ice fishing in the middle of a frozen frictionless pond, and you're stuck on a frozen frictionless pond, right? You try and walk, but it's frictionless, so you can't walk, right? What would you do knowing Newton's third law, what would you do to try and get out of this pond? Okay, pause the video and think about it for a minute. Okay, I'm going to take it that you paused the video, you thought about it for a minute. Here would be my solution. Okay, you got these big heavy red boots on, right? If you take something, some object, and launch it in one direction, right? Accelerate it in one direction and let go, then you have to exert a force on that thing to get it thrown out away from you, right? And that thing is going to have exert an equal and opposite force on you, right? So if you say take off your boot and you throw it, then you should kind of go back the other way. Okay, so you and the boot are going to go in opposite directions. You place this force on the boot that goes that way, and there's an equal and opposite force exerted on you, pushing you back in this other way, right? I used U for you and B for boots. So Newton's third law then tells us that the two forces are equal in magnitude and opposite in direction. Okay, here's the magnitudes of these two vectors, right? Just reminding you of the notation when I drop the arrow over the top, then that just refers to the magnitude of the force. So you can see here, right, the magnitude of that force on you by the boot is equal to your mass times your acceleration, right? And the force on the boot by you is the mass of the boot times the acceleration that the boot experiences, okay? By Newton's third law, we know these two things are equal. So the product of the masses and accelerations for both you and the boot are equal. Well, that would mean that your acceleration is equal to the ratio of these two masses times the acceleration of the boot. Okay? So that means, yeah, the mass of the boot over the mass of you. This ratio is really, really tiny. You weigh way more than the boot does. Okay? So this is going to be a lot less than 1. Okay? And that means your acceleration is going to be small, right? Your acceleration is going to be way smaller than the acceleration of the boot. So it's going to take you a while. It's going to take you a while, but you're not stuck. You can get out of the frozen frictionless pond slowly. All right, let's talk about free body diagrams then. What a free body diagram is a diagram of your problem where you've labeled all of the forces and they're all pointing in generally the right direction. Okay. In a free body diagram, it's really important that all forces get an arrow, and there should be no arrows on a free body diagram that aren't forces, okay? So don't put any velocity vectors on a free body diagram. Don't put any acceleration vectors, nothing like that. You're not even going to put a net force on a free body diagram. You're just going to put all of the individual types of forces that are involved in a specific problem. So there's 4 different types of forces you're going to want to look for to put on your free body diagrams for right now. Later we'll get to friction and other forces that are like spring forces and things like that. But for now, just tension, weight, applied forces, and normal forces. Okay, tension, you know about tension, right? Tension is the thing that happens when your professor is going over time in his lecture and everybody's upset about that and wondering when he's going to stop. That's one kind of tension. There's another kind of tension that goes on your free body diagrams, though, and that's the force that's carried by a string, right? So tension in strings brings about a force. So tension forces, it's important to remember that the magnitude of the tension force is the same everywhere along a string, okay? Tension forces pull, they never push. And but you can use, say, things like pulleys to redirect the direction of forces. So here I have an example, right? I have one box here that's connected by a string over a pulley here. Okay, this is a little pulley there. And it's connected to another box there. Now, the magnitude of the tension force is the same everywhere along the string, which means that, so if I take red to be the color of the forces that I'm going to draw in my free body diagram, so there's going to be a tension pulling up there. Okay, I'll label that T. right, there's also going to be a force exerted on this box there, right, that's going to have the same magnitude, T, right, but obviously it's pulling in a different direction there, right? And so long as the pulley is massless, it's an ideal pulley, then those two tensions forces are going to be exactly the same. Okay, so this is important. Massless strings and ideal pulleys are the things that serve to redirect these forces, and they show up a lot in our problems. Okay, number 2, weight. Okay, so this is, when I say weight, I do not mean mass. Things that are massive and are in the presence of some gravitational body have weight, okay? Weight is mass times gravity, for the most part. You can watch Walter Lewin's lectures to see that it's a little bit more complicated than that. Like when you're in an elevator, you could argue that weight is different, right? The thing that a scale would read while you're accelerating upwards would be greater than actually mass times gravity, but that's besides the point. So for the most part, you're going to have weight that's equal to, right, or the force of gravity that's equal to the mass of an object times little g. Okay, little g is the acceleration due to gravity. So for something that so we know that force is mass times acceleration, right? Even if something is sitting, say, resting on a table, or if I take this book here, right, and I just set it there on my hand, okay, the book has a gravitational force pulling down on it that's equal to its mass times little g. Even though it's not accelerating, it still has that force there. It's just that the force of my hand is pushing the thing up, so that the net force is 0. On my little diagram here with the 2 boxes, I've already included the tension forces. Now, if I'm going to put the weight on there, right, I would put it down like this. And I would say, since this is mass 1 here, I would call this Fg1, and this is mass 2 here, I would call this Fg2. Okay, so the gravitational force on M1 and on M2. Now note, right, the tension here, the magnitude of the tension force was exactly the same, so I put the same symbol on there. I put T for both of them. Here, they have, in principle, they could have different masses, this M1 and this M2, so I put Fg1 and Fg2 on there and labeled them with a different index to show that they could have different forces on the Freebody diagram. Okay, so that's weight. We've done tension and weight. Now, applied forces. Those are the simplest ones. This is just like, say that this guy comes in and he pushes on this mass there. He introduces some applied force. Right? This way here. And so we'll call that FA, F applied. An applied force is just some force that gets introduced and really doesn't get explained very much. So something like a push. And finally, the normal force. Now, the normal force, the word normal, it just means perpendicular. Okay. So normal forces are exerted perpendicular to a surface. Okay. So here my box is sitting on the ground. M1 up here is sitting on the ground. So the normal force would go up. It's exerted by this surface on the box that's resting on the surface. It points up against gravity there. Okay, what about M2? Well, M2 is suspended in the air, so there's no normal force on M2. Something to keep in mind is that, you know, if you have some kind of an inclined plane or something like that, the normal force is not always up straight against gravity. It's always perpendicular to some surface. Okay. All right, so I have labeled all of the forces here that are involved on this particular example problem. They're all there in red. So this is the Freebody diagram. Now, you're going to get problems on your homework and on exams and stuff that look like this, and then they ask you to solve for certain things. But the first part of those problems usually are just going to have something like, part A, tell me what is the Freebody diagram. And you have to draw it exactly like this. Okay, let's do some other examples. So, where I'm just going to get the Freebody diagram. So here I have Tarzan swinging on a vine through the canopy, through the forest. What forces are involved here? Pause this video and draw them yourself. Okay, now I will do it. So this is Tarzan, he's swinging through the forest, right? He has weight, right? There is a gravitational force pulling down on him. There is also a tension force that acts along the string, pulling him up in this direction here. So there's an Ft, a tension force, and Fg, a gravitational force pulling straight down on him. And one other thing that I would recognize, or that I would recommend that you do, is get rid of this thing, okay? Because all arrows, all forces get an arrow, and no arrows that aren't forces, right? So I had that little arrow on there to show you which direction he was swinging in, but that's not a force, so I don't want to include that on my free body diagram. Okay, just want to make sure that this is clear, that this is F sub G, right? Gravitational force, or the weight. Okay, now what about this one here? If I have a person pushing here against this box, what would the free body diagram look like? Pause the video, try it out yourself. Okay, so there's an applied force that's pushing on the box in this direction, force applied, and there's weight, the box has weight, so there's a gravitational force pushing down. And finally, since the box is resting on a surface, that surface is exerting a force on it, so there's a normal force pushing up. That's normal. Okay, I'm taking this to be a frictionless surface since we haven't talked about friction, right? If somebody was pushing on a box resting on a surface and it wasn't moving, say, then you would know that there's got to be another force in this direction to keep the thing from accelerating, and that must be then the friction force. We'll talk about friction in the next chapter. Okay, so I have the exercises that I'm going to go through next posted as a PDF in the description down below the video. So you can download that and take a look at 28, which I also have here up on the screen. Start that yourself, hit pause, and then come back and see if you got it right. Okay, I'm going to take it that you did that. Now let's try and put the right force vectors on here. So we have one basketball player jumping in the air and one on the ground. So I remember this series actually from when I was a kid. So Tim Duncan's the guy on the ground, right, with his feet on the ground. Ben Wallace is the big dude with the afro who's jumping up in the air. So since Ben Wallace is up in the air, there's no normal force on him at all, right? And that means his free body diagram is pretty simple. There's just one force of gravity pushing down on him. All right, so that's pretty simple. Tim Duncan, he's standing on the ground, so there's going to be not only a gravitational force on him, but there's also going to be a normal force. So that's the extent of the problem. That's what's asked of you. There's something else that I would like to point out about this, though. So let's just say that we knew that Tim Duncan was either going to stay on the ground or that he was currently moving upwards. His center of mass was moving upwards, and he was leaping up off of the ground. What would that mean for our forces here? Well, the normal force is pushing up, right? So I could write the vector as its magnitude in the plus y direction, and the gravitational force here on Tim Duncan, so Tim Duncan is the one who's standing on the ground, the gravitational force vector is, I could write it as its magnitude times minus y, because it's pointing down. So if I wanted to write then the net force on Tim Duncan, right, it would be just the sum of these two forces here, Fn plus F gravity. So if I take those two things, add them together, I'll write it in terms of its magnitude with the proper directions. So Fn minus Fg, right, in the y-hat direction. And since this is a net force, I can set this equal to his mass times his acceleration. His mass times his acceleration, A. So if I knew that he was jumping, that would mean that his acceleration is positive. So that would mean his mass times his acceleration is positive. And it would also mean that this quantity here was also positive. Okay, well, if that's positive, that would mean that Fn minus Fg is positive. And that means that the normal force would have to be larger than the gravitational force. So if we knew that he was jumping, that implies that we know that the normal force is greater than the gravitational force. Otherwise, he wouldn't lift himself up off the ground, right? Okay, now, what if we knew that he was just standing there, not accelerating at all? Well, that would mean that the normal force was equal to the gravitational force. What if he had just gone up for a rebound, and at this moment he's actually crouching down? His acceleration is going downwards towards the floor. Well, that would mean then that the gravitational force is actually greater than the normal force, right? And that's not because he gets any less weight on him, right? It means that the normal force on him is lessened because he's accelerating downwards. He's not pushing then against the floor as much as he would be in the jumping case, right? In the jumping case, the normal force is greater than the force of gravity. And if you think about it, that makes sense. If you jump, if you stand up off of your chair and jump right now, you will feel a force, the force that you are pushing down against the floor, and then hence the force that the floor is pushing up on you, will feel greater when you're jumping up off the ground. So that's a little bit more about what's going on here. And this is going to be a common theme that we'll find the normal force or the tension force in different free body diagram problems by what we know about the system and what we're given in the problem. Certain things like, well, we know that he's jumping, can tell us more than you might expect. All right, next up, I'm going to do problem 27 there. You can do these steps, these first 6 steps, before I ever start doing anything. You can pause the video after I'm done explaining the steps and do them, and then I'll go through and do the problem. Okay, here's the first 6 steps basically that I would follow for any problem, but especially for these free body diagram problems. Step 1, read the problem. Just read it. Step 2, really read it. Okay, read it again, and this time while you're reading it, the first time you're just going to read it. The second time, you're going to really read it, which means you're going to think really hard about it. You're going to underline and circle things that you think are important. My strategy was always underline important bits of information, circle given, circle known values. Okay, after you do that, you're going to draw a free body diagram. So this, like I said, this list is pretty good for any type of problem. So for number 3, you can just put in draw a picture. You want to just talk about any general problem. And then, and remember to include all of the forces that you can pick out that are involved in the problem. And don't put any arrows on there that aren't forces. Then part 4, write down what was given. And part 5, write down what do I need to find. Make sure that you really understand what you need to find. And when you write down the givens and what you need to find, write them down in terms of symbols, right? They're given to you in words, in the words up in the statement of the problem, but I want you to write them down in physics symbol terms, okay? And then step 6, use your intuition. Think about what you know. A lot of these problems, like this one, have things in them that, well, you've seen things like this before, or at least you have an intuition for how these types of things work. When there's a box on one side, something goes over a pulley, and there's a weight on the other end. You kind of have an intuition for how a system like this might function. So think about the problem, conceptualize it in step 6, and then I will solve the problem once you're done doing that. Okay, so hopefully you did those steps. Now I'll walk you through the ones that I did. So first I read the problem, then I read it again. I like to underline helpful information and circle given quantities. Then I drew my Freebody diagram. Okay, now I have MB for the mass of the box and MW for the mass of the weight over there. And you can see, right, I've labeled all the forces. So each one has a force from gravity pulling down, and each one has a tension force pulling up. Right, there's a tension force there, and there's a tension force there. And there's also this normal force here on the box, which is resting on the surface. No normal force on the weight because it's not resting on a surface, right? There's just tension and gravity, otherwise known as weight. Now, you're supposed to write down the given quantities. Okay, I know we were given the force of gravity, right? We were given the weight for both the box and for the weight, right? The force of gravity on the box was 77 newtons, and then the force of gravity on the weight was different, right? Part A was 30 newtons, part B was 60 newtons, part C had it at 90 newtons. Okay, and we were asked then to find the normal force, right? The normal force on the box, the force that the table exerts on the box. So I followed all of those steps. Now I want to explain what my next series of steps are going to be. There's a lot of steps to these Freebody diagram type problems. Okay, the first one, this is how I like to do it in this order. I like to write down Fnet equals ma for each object, summing over each of the individual forces first, okay, in their vector forms. So this should actually have a vector form here, because that sum will be true regardless of which coordinate system I pick. So I like to write this down first. After I write down my Fnet equals ma equation, I like to write down and pick a coordinate system. Okay, now notice this little asterisk here means that these steps should be performed for each object. You can pick a different coordinate system for each object, and you'll see when I solve the problem why I'm making such a big deal about this, because it actually does make a difference for this exact problem. You want to pick a coordinate system that can have this box moving up correspond with this weight moving down, right? That's because you use your physical intuition, you've looked at this and thought about it, that should make sense to you why that would be helpful. And that comes in at the level of your coordinate system. Then step 3, I like to take Fnet in the x component after I've chosen my coordinate system. I like to take Fnet equals ma from its vector form into its individual components, into its x and y components. So notice here, this is also for each object. So I have 2 objects. In this case, I only have one dimension. There's only one coordinate. Everything's either moving up or down. But in other problems, you might have x and y components that are important. If you have multiple, let's say you have 2 objects and you have 2 coordinates, you're going to end up then with 4 equations here. So make sure that you have them all. Okay, the next thing I like to do, step 4, count the number of knowns and the number of unknown quantities. Okay, make sure you have enough information before you start messing with equations, because people do this on tests all the time. They sit there, and they do tons of math, and they never realize that they got tripped up and right up here at the top because they never got enough equations in the first place. So there's no point in sitting there and doing a ton of algebra if you don't have the same number of unknowns as you have equations. So this is really important. Step 5, solve the equations and do that in terms of symbols, okay? Don't plug in numbers until the very end. It'll make your life a lot easier. So solve the equations for whatever you're supposed to find. Step 6, plug in the numbers and make sure to keep your units along with the numbers so that you'll know the units of the final quantity. Most of the time it's going to be in terms of SI units anyway, but keeping your units is a nice check to make sure that you didn't drop some factor or something. If at the end you're supposed to find a force and it comes out in units of meters per second squared, then you must have at some point forgotten a mass, dropped a mass. And so if you keep your units along in there while you plug in numbers, you will have that nice check on your answer. Okay, and then finally, step 7, check your answer. And there's a lot of different things that you can do to check your answer. You don't have to use Google. That's not what I mean by checking your answer. Okay, what I mean is use your intuition, use rough estimates, and use certain limiting cases. Okay, here's what I mean by this. Intuition. Does it make sense? Does it make sense? So if I came up in this problem with an answer that said, say that this box is going to accelerate, have a negative acceleration, and I picked the coordinate y going up, so negative acceleration means that this box is going to plunge through the surface here. Okay, that doesn't make sense, right? Your intuition tells you that the box is not going to plunge through the floor, so this would be this would tell you that you've done something wrong and you need to go back and rethink something, right? Likely a coordinate problem. Next thing you can do to check your answer, rough estimates. Okay, so if you're asked in some problem, say, to find the speed that a car is moving from one city to the next, and you find that the speed is like half the speed of light or something, well, you probably did something wrong. If you're asked to find the time that it takes to drive from New York to San Francisco, and it takes 4 seconds, you probably did something wrong, right? You can use your own rough estimates from just thinking about it. Final thing, limiting cases can be helpful. So I'll give you examples of these later, but say there's an example. So here's a good example of a limiting case. So in this problem here, right, we have a box resting there and we have a weight over on the other side. A nice limiting case would be if you take their weights to be equal, okay? You can find answers for, say, the acceleration of the system in terms of their two masses, and then you can just say, well, a good way to check my answer would be, does this make sense if I say that they both have the same mass? If you have some factor of, say, mb minus mw in the denominator of your acceleration, then the limiting case that I've chosen here, right, where the two things are equal, well, that would mean that if you have an mb minus mw in the denominator, that would go up to infinity, right? The acceleration would. So that's an example of a limiting case that you can use as a check on your answer. You know that that can't be right then, and you have to go back and rethink some things. So checking your answer can be really, really helpful for you. And just a few other, just to drive this home one last time, make sure you do an F net equals MA for each object. Make sure you set up your coordinate system for each object, and make sure that you apply that consistently. And number 3 there, make sure that you break these things into their individual components and do that for each object. And finally, before you start going into solving your equations and where you're going to spend some time sitting there and doing algebra, make sure you count the number of knowns and the number of unknowns and make sure that you have enough equations, right? You need, if you're going to solve for 3 unknown quantities, you better have 3 equations. Okay. All right. So we're back. I'm going to solve the problem now. Just had to erase the board because we're kind of limited for board space down here in the physics basement. But I have it up on the screen for you. I'm going to solve the problem going through these steps. All right, step 1 was to set up an F net equals ma equation for each of the individual objects. So I have F net on B. That's equal to, right, just looking at the free body diagram, I have a force of gravity, I have a normal force and a tension force. So Fn plus T plus Fg. Note that this is true independent of whatever the coordinate system is. Doesn't matter what the coordinate system is, that's still true in its vector form there. Now, F net on W is just, there's a tension force and a force of gravity. Right? There, that's step 1. Step 2, pick a coordinate system for each object. Okay, this one is kind of tricky for this particular problem. So, if you look over here, you'll note that I have chosen for object B a coordinate system where plus y is pointing up. Okay, y is up for mass B. For mass W, plus y is pointing down. Now, why did I choose them to be pointing in different directions? The reason is because I'm setting things up based on my intuition. I know these 2 objects are tethered together. Okay? That means they're going to have the same acceleration. If this one, if MB accelerates up, MW is going to accelerate down. Okay, the magnitude of that acceleration is going to be exactly the same regardless of what the coordinate system is. Whatever coordinate system I pick will not affect that. However, if I choose my coordinate system nicely, where plus y is going up here and plus y is going down over here, then they'll have the same direction in addition to the same sign. So that's really nice, because what I'm going to do when I set up these, go on to the next, okay, so I'll continue to explain that as I go into the next step. So in step 3, I'm going to pick the individual components out, right? Thankfully, this is a one-dimensional problem, right? There's no x forces involved here, so I can just set these things, F net y, in terms of, right, this will be equal to mass B times A, and this will be equal to mass W times A. Right, so there's only, the acceleration only has one component. Now, you'll note here, if I would have chosen this coordinate system differently so that y was, say, going up for both cases, I would have had to put a minus A in here in order to make this consistent, because I would have had to have one going up correspond with the other one going down. So this is one thing that you learn from doing a lot of these problems over and over again. But another one of the things that's one of the reasons why I gave you this long list that includes number 7, right? Number 7 is right there on the screen, right? It says check your answer. Well, if you would have done this and flipped the axes around the other way and solved the whole thing without putting the minus A here in the end, what you would have is something that, upon checking your answer, by setting the 2 masses equal, right, that limiting case check that we talked about, you would see that the answer you got doesn't make any sense. And then you might think, maybe I need to pick a different coordinate system, or maybe I need to be more careful with my signs when I put these things in. Okay, something to keep in mind. So I have F net in B is equal to MA, and I can put that in terms of the individual forces, and now I need to be careful to make sure that the signs match up, right? So Fn is pointing up, so it's positive. T is pointing up, so it's positive. And the force of gravity on B is pointing down, so that one is negative. Minus Fb. Okay. For the mass of the weight, it's equal to, right, there's a tension force that in this case is pointing in the negative y, direction, right, minus the tension force, plus then the gravitational force on W pointing in its positive y direction. All right, so that's step 4. And now I can, sorry, that's step 3, and now I can go on to step 4. Let's count the number of equations I have and the number of unknowns. So I have 1, 2 equations. I'll label them 1 and 2. And I have, well, let's see. This is a known. This is known, right? The acceleration, that's unknown, right? The normal force here, that's unknown. That's what we're asked to find. And the tension force there, that is also unknown. So we have 2 equations, and we have 3 unknowns. Okay, does that mean that we're sunk, that we can't solve this problem? Of course not. Okay. Whenever you find yourself in this situation, I have 2 equations and I have 3 unknowns, that means you need to think. You need to think a little bit more. So let's use our intuition and let's think about this problem a little bit more. Okay. I'm given FGW for part A, B, and C with 3 different values. Okay. I know something about this system just from my own physical intuition. I know that this weight here, if this one is larger than that one, if this object, the weight here is more massive than the box, then the whole system is going to, this thing is going to fall and that's going to go up, right? And I know that if the mass of the box is larger than MW, that this thing is just going to rest here on the table. So that's something I know. Okay, well, let's think about this. Part A and part B both have FGW is greater, FGW is less than FGB, right? So for A and B, we have FG for the box is greater than force of gravity for W. Okay, if the weight of the box is larger than the weight of the weight of the counterweight over here, then what is the acceleration of the system going to be? Think about it. That one weighs more than that one. That means that thing is just going to rest there on the surface, and that means that the acceleration is going to be 0, right? The acceleration is going to be 0. So that gives me a third equation, a really helpful one, right? That gets rid of 2 of them. So let's just do part A and B first. So in that case, right, both 1 and 2 are equal to 0. So I have 0 equals Fn plus T minus FGB, and I have 0 equals minus T plus FGW. Okay, I can do addition or substitution method, right? Here I have 2 equations, 2 unknowns. I can use addition or substitution method to find my answer. I'm asked to find Fn, so what I'm going to do is just take this equation and add it to this equation. Okay, I'm going to use the addition method. So if I do that, adding the left-hand sides are just, they're both 0, so they add together to be 0. The right-hand side, I get an Fn plus T minus FGB, first equation, plus this minus T plus FGW. Okay, now notice that the T and the minus T cancel each other out. So I get that this is equal to Fn minus FGB plus FGW. And in other words, the normal force is equal to, adding across those other 2 terms, F, the force of gravity, B minus force of gravity, W. Okay, this is exactly what I was asked to find. So let's just plug in the two numbers. So for part A, right, that means Fn would be 77 newtons minus 30 newtons, right? That's 47 newtons. In part B, right, it would be 77 newtons minus 60 newtons, which is 17 newtons. Okay, and so I can box in my answer. I have no room to write down part B, but that's fine because it's really pretty much the same as part A. And now I'll erase the board and we'll do part C. Now, in part C, FGW was 90 newtons, and that meant that this weight over here is heavier than this box here. And so, as I have shown here, now I want you to stop, pause the video for a second, and tell me what is the third equation that I get because I know this. Okay, I'm going to take it that you've done that. Now, I'm going to go through and just talk my way through it. If this thing is heavier than that thing, then the whole system is going to move, right? The weight here is going to fall. The box here is going to lift up. Now, if that box lifts up off of the surface, then that means the normal force is 0, right? The normal force would be 0. So, the normal force for part C is 0, and that is our final answer. Okay, but before I let you go, so that this is the final answer, the problem is done. But before I let you go, I do want to talk a little bit about this case and if we wanted to solve for the acceleration. So, going back to our FNet equations here, in the case of part C, right, where the normal force is 0, then I can solve, then my equations here reduce down to, for mv times a, it's tension minus the force of gravity, and for mwa, it's force of gravity minus tension. And I can do the same addition method. What I end up with is, on the left-hand side of the equation, an mv plus mw times a equals a difference between the two weights, right? It's this weight minus that weight. Okay, that makes up the net force on the system as a whole. Now I'm going to get ahead of myself a little bit and just point out that this equation right here is actually the Fnet equals ma equation for the system as a whole. This is the total mass of the system, right? It involves two objects. This is the acceleration of the system. It's the acceleration of the center of mass of the system. Okay? And here, these are the external forces. So the tension, right? Notice that the tension pulls in two directions, internal to the system, right? So that's considered an internal force. And we know, right, that Fnet equals ma, and those are external forces that we're talking about, right? Internal forces. So Newton's second law, or Newton's first law says, an object in motion will remain in motion unless acted upon by an external force, right? If you consider the system as a whole, with both masses included in it, then that tension is actually an internal force. That's why it's pulling in different directions. Okay, so that was getting ahead of myself. Sorry. Now let's move on. Now, if I solve this then for the acceleration, I have the difference between these weights divided by the masses. And if I put those then in terms of the masses here, I have mass of the weight minus mass of the box times little g over the sum of the two weights. Okay, so you notice here then I have a sum of weights in the denominator and a difference between the two masses in the numerator. Okay, and I was given the force of gravity on each one of these, I would just have to divide this by 9.8 in order to get, right, the mass here. Okay, so let's just do some sanity checks on this, because I do want to get all the way down to number 7. Okay. Number 7, some sanity checks. Well, I already said before, a good sanity check would be, what if MB equals MW? Well, if MB equals MW, and we're in this case here where the normal force is 0, okay, then what's going to happen to this system? It's just going to sit there, right? If that weight and that weight are exactly the same, then this MB is just kind of going to be hovering above the surface, right? The normal force is going to be 0, but the acceleration is also going to be 0. And there's a difference between the two masses there in the numerator, so if they're the same, the acceleration of the system is 0. Okay, so that's a good check. That's a good check. Now, what about other checks? What if MW is really, really large and MB is really small? Okay, that means the acceleration would be really large, right? If MW is way bigger than MB, and that's exactly what I get here, right? The acceleration would be really large if MW was big and MB was small. And in the reverse case, right, then we're no longer in this regime where Fn equals 0, so that would not be a good sanity check, right? That would have been a good sanity check on the for the equations that we had derived under parts B and C. Okay, so I went through this problem really slowly because I wanted to show you all of these steps. I also wanted to give you a problem right up front where it makes being careful about the coordinate system really clear. And now we'll go on and do some other problems a little bit more quickly. Hello everyone! Okay, last problem, and I'm going to try and go through this one kind of quick because this video is getting a little bit long. So before I forget though, this is the first time that I'm using this whiteboard. I got like a lot of lights in here now. Please do comment in the video below, below here, and tell me, can you read this okay? Is this good? Do you like this? Or do I need to write bigger? Something like that. I prefer this, so let me know. All right, let's do this problem quickly. Okay, let's say that you have two boxes, a red box, mass mr, and a blue box, mass mb, right? Red for R for red, B for blue. And they're sitting on a surface, they're touching each other, and there's an applied force Fa that is pushing on them. Okay, and so let's say that you know the applied force, you know the mass of the red box and the blue box. I want you to find the acceleration of the system, and I want you to find the force on the red box by the blue box. Okay, just in terms of these abstract variables, Fa, Mr, and Mb. Okay, and then I gave you numbers to plug in to find the magnitude of that force as well. Okay, pause this video, solve this problem, put your answer in the description below if you're so bold, and then I will go through it. Okay, let's go for it. Now, all of the steps I've gone through, right? I wrote down the givens and what I'm supposed to find. I've used my intuition. I know that if a force is applied and it pushes on these two box systems, that the two boxes are going to accelerate in that direction, right? This is a nice, easy, one-dimensional problem. That's really nice. Let's first write an F-net equation for each one of the boxes. Well, we actually have to first do a Freebody diagram for each of the individual ones. So for MR, we have an applied force Fa going this direction, and we have a force that Mb exerts back on Mr, pushing in this direction. Okay, I'll talk about how I know that in a minute. Right, F on R by box B. Here, box B, does Fa act on box B? No. Fa is acting on Mr, right? The only force that's acting on Mb here is going, right, in this direction, right? It's the force that's the force on box B by box R, right? The force on the blue box by the red box is pushing it that way. Now there are, of course, also normal forces for both of these, and there are weights for each one, right? But notice that I actually don't need to know these. This is a one-dimensional problem, so you don't actually need to know those things in order to solve this. It's fine. So, right, of course, the normal force and the force of gravity, they're just equal in magnitude and opposite in direction, because there's no acceleration in the y direction up here, right? That's y, and this is x, right? I'm going on now to step 2. There's no acceleration in the y direction. These boxes aren't leaping off the table, nor are they plunging through the surface. Okay. So, so there's only one force in the x direction that's acting on MB here, and it's the force that box B exerts on, or the force on box B by the red box. So notice here, I have an FBR and I have an FRB. Okay, we know from Newton's third law, right? N3 implies that FRB is equal to FBR. I'm sorry, equal and opposite to FBR, right? And so that means, right, they're equal in magnitude. FRB equals FBR. Right here, I've expressed this. These are just the magnitudes, right? They're equal in magnitude, and they're opposite in direction. Okay, great. I'm just going to make sure that everybody can see this. There is a minus sign there. Okay, good. Now, let's go and do step 1. So, step 1, I'm supposed to do an F-net equation for each one of these. F-net on B is just, it's F normal plus F gravity plus the applied force, oops, sorry, I'm doing box B there, plus, right, FBR, okay, and F-net on A is equal to, there's a normal force, there is a gravitational force, and there is an applied force, A, right, and there is this force that is exerted on the red box by the blue box. Okay, so this is great. Now, I already have my coordinate system set up, right? The positive x direction is going to be where the action is, right? That's the way they're going to accelerate. And I've already laid out the implications of Newton's third law. So Newton's third law wasn't, we didn't talk about it a lot in the earlier example problems, but it comes in and it's important here. And this is the type of thing that students need to know. This is one of the ways in which you need to be able to apply Newton's third law. So let's now go on to step 3. And like I said, I'm going to drop the y components because they won't affect anything. So the net force in the x direction is going to be, now remember I got to keep my signs straight here, for B, it's going to be mb times a. Now note again, the accelerations are going to be the same, right? The two things are touching one another, so the accelerations for A and B are going to be the same. That's not always the case, but it has been in the last 2 problems that we did. mb times A, the acceleration of the system, is equal to, and this is in the x direction, right? It's going to be FA, right? FA is in the plus x direction, so this is a positive, plus, now FRB is actually going in the opposite direction, right? I'm going to do minus FRB, because FRB is pointing in the negative x direction there. Okay. Also, Fx net on the red box. Sorry, up here I was doing the red box. Here I'm doing the blue box. So the blue box, the second box over there, it's mass of the blue box times A equal to mass of the blue box times A is equal to just FBR, right? And that force is in the plus x direction, so that's good. All right, now I have two equations. Going on to step 4 here. I have two equations. How many unknowns do I have? A is unknown, right? I was told to take FA, MR, and MB as givens. So, given, given, given. Okay, A is unknown, FBR and FRB are unknown, right? So, does that mean that I have 3 unknowns? No, right? It means I have 2 unknowns because by Newton's third law, right, I know those two things are equal. So, I can solve these. I will take them, these two equations here. Here, we'll call this 1 and we'll call this one 2. I'll take the 2 and I'll add them together. Right? So if I do that, I take 1 plus 2, and I add these two things together, I'm going to get MB plus MR times A on the left-hand side, and on the right-hand side, I'm going to have just an FA, right? Because these two here are equal. There's a minus there and there's a plus there. So I'm going to end up with this equal to the applied force. Okay. Now, again, I have the total mass of the system times the acceleration of the system equal to the external force here. Right? The Newton's third law of pairs are internal forces that cancel out. Again, I'm getting ahead of myself when I say that. So that means I have the acceleration equal to FA over MB plus MR. Great. I have an acceleration, right, in terms of the force and the two masses, which I was supposed to take to be given. So, acceleration, done. All right, I'm going to erase this because I need some more room. Eventually, I'm going to start asking for people to donate to my Patreon account so I can get another whiteboard or something. But I'm not going to set up a Patreon account because I'm not going to kid myself. Okay, now I'm supposed to find FRB. So I found A. I can just take A and plug it in to find FRB, right? So I can use equation 2, right? But remember, so MBA equals, it's FBR here, but that's the exact same thing as FRB, the thing that I'm supposed to find. So instead just equal to FRB instead. And that's totally fine. The only reason I put it in there is because it's the same as that, and technically this is what I was asked to find. Okay, and now I can substitute in the A that I just found into this equation. Right, so here I have FRB equals MB times whatever I just found for A, and I think it was FA over MA plus MB. Okay, there. I have now FRB all in terms of known quantities. And the last thing I was asked to do was to plug in these values. So if FA is 4 newtons, MR is 3 kilograms, and MB is 1 kilogram, then I have this force would then be 1 newton plug in those numbers. Okay, I hope that was a helpful example problem for you when Newton's third law is important for finding the answer. And I hope that all of these example problems were helpful for you. You're going to have some one-dimensional problems like this on your homework, and on Monday I will give you a video that has two-dimensional problems, Freebody diagram problems. Have a good weekend.